All right, so today, the good news is we're kind of mostly done with all of the integration techniques. So we're going to start something quite a bit different, which is numerical integration. Really has nothing to do with anything else in this class, but one of the most important things, or one of the three most important things in the entire class, because most people don't ever sit at a desk and do integration by hand, like we've basically been doing the last couple of weeks. I can almost guarantee you that unless you become a professor, you're not going to ever really do an integral by trig substitution in your whole life on a job. However, numerical integration is like the backbone of how math really gets done. Because what really does happen is you use a computer or use a calculator. Well, how do all those things know what an integral of something is? And the basis for that is what we call numerical integration. So the idea here is that we're going to be approximating integrals when we can't find an antiderivative. So when you can't find an exact antiderivative by hand. And perhaps more accurately in real life, this is just how you do it, right? Again, you're probably not going to really take many derivatives out. Now, besides the fact that it's just the most common way to do it, let's take a look at examples where you physically have to use numerical integration. So suppose I gave you something like e to the x squared. Very common looking integral. It's actually a fairly important thing, actually. This also is an example, but e to the negative x squared becomes one that's very important in statistics. And you cannot physically integrate that thing. There is actually no antiderivative that exists. Nothing, no matter how complicated you want to look at it, if you took its derivative, would get back to that. So you're really stuck unless you do this. Another thing that's actually pretty common is trig functions with the argument squared. So we know how to do sine squared x, but sine of x squared, literally impossible. So these things are both impossible by hand. So even if we wanted to do things by hand, we could. Here's the solution to basically what we're going to do, is we know that the integral of something is associated with the area under the curve of that thing. So what we're going to do is we're going to divide up the area under the curve into geometric shapes that we know the area of, and then add up the areas of those shapes. Now we can make the widths of those shapes very small, which will give us better and better approximations. That's the basic idea. We'll just approximate the area under the curve by other shapes. Here's what in general that would look like from a calculus perspective. So in general, you can evaluate a definite integral. So the integral, say, from a to b of f(x) with the x by doing just what I said. I'm going to divide up the range, which, if it's an integral from a to b, the range on which we're finding the area under the curve is from a to b. And we're going to divide that up into n subintervals, where n is our choice. And they're going to be of equal length. They don't technically have to be, but it makes it a lot easier, and there's no real reason not to do it. So if they're going to be of equal length, then we know that that length, the delta x for each of the regions that we're going to divide it into, is just the range, b minus a, over however many intervals, so b minus a over n, so that, in the end of the day, we can approximate the integral from a to b of f of x dx. That's the thing we're trying to solve. And it's approximately equal to a summation. So let's say I equals 1 to n, going over all of the subintervals that I've made, of f of x sub I times, I'm going to say f of x sub I star, times delta x. So this x sub I star is some position in the ith interval. So I'm going to say it's some point in the ith interval. Now there's different techniques whereby that point is different. That's the basic idea. And so if you can imagine, here's some curve, we'll do a bunch of these in a second, you have to copy this one down. If I wanted to find the area from A to B, I'm going to divide it up into a couple different things, and I'll take each width times the height somewhere in that interval, and kind of like multiply it across to say, let me add up the area of those boxes or something like that. And that's about the area under the curve. That's the basic idea of numerical integration. Now there's going to be 5 rules or schemes where we can do this. The 2 at the end are going to be by far the most important. The first 3 are more just like baby rules to get our feet wet of seeing how this would work. No one actually really ever uses these, but here are the several rules. Let me do the basic ones first. And I'll basically put what the summation would look like, what a graph of it would look like, and we'll go from that. So again, remembering that we're going to look at different heights at different points in that interval, the 3 most obvious points we can look at are the left, right, and middle endpoints. So the left endpoint rule looks like this. So what I'm going to do is I'm going to create the same little parabola over and over and over again, and we'll divide it up in all these different schemes. Let me see how far. That's about as far as I can. So imagine that I'm dividing this up into 4 intervals. All right, so I want the area under this curve. The first interval goes from there to there, and it's starting at A, ending at B. Second interval goes from there to there. Third from there to there. Fourth from wherever that ends to B. Okay, so we're going to call these little spots x sub 0, x sub 1, x sub 2, x sub 3, and x sub 4. Those are all the dividing points between the intervals. We'll be able to easily figure out what those are in a bit. What the left endpoint rule says is let's approximate the area under the curve by saying that the height of a rectangle that I'm going to approximate this area with is going to be the height of whatever the left endpoint is. I'll take that area as my approximation there. That area is my approximation there. That area as my approximation there. And that area is my approximation there. You'll notice that it's not a great fit, and definitely makes some errors. The good news is you can see that the errors are in either direction in this particular curve. Right? As we were going in this direction, the first 2 boxes we underestimated by quite a bit. The next 2 boxes, it looks like we overestimated a little bit. So if you have a curve that's going up and down, maybe all those things would cancel out, maybe not. If you just had a curve like exponential that was always increasing, you'd always make the same type of error, so it might not be great at all. But that's why it's not a great rule. The left endpoint rule, we call it L sub n being the number of intervals that we've chosen, is going to be this. The summation from I equals 1 to n of f of x sub I minus 1. So notice the first height is at x0. So if we're in this thing from 1 going up to n, to get to the 0, so you got an x of 1 minus 1. So that'll give us x0 right there, times delta x. All right, so that's basically what we do. It's a x0 times delta x plus x1 times delta x plus x2 times delta x plus x3. And that is, well, like I said, not a good approximation, but it's an approximation of the area under the curve. Then do the right endpoint rule. Any questions with it? There's one thing here. Yeah, the lights, I wrote in the light a little bit there. Yeah, I'll not write in those boxes again. So just the thing that you cannot see, perhaps. This says numerical integration, and this up here just says several rules in parentheses, basic rules. Box that. Any thoughts with that stuff so far? Second boring rule is the right-hand rule. All right, so same curve, and we're going to divide it into the same 4 ways. And now in this curve, when I look at x0, x1, x2, x3, x4, the height that I'm going to use at each interval is whatever is on the right hand. So it's the exact problems that we had before, but reversed. On the way up, we had overestimations. On the way down, we had underestimations. Maybe all those things would cancel out. We got a nice curve that moved up and down, like a sine curve maybe. But some wouldn't. So the right endpoint rule would look like this. It'd be the summation from I equals 1 to n of f of x of I times delta x. Because the first one we use for the first interval is the x1 point. So x1 times delta x, x2 times delta x. And I'll put up the midpoint rule as well. Same curve, I mean, you can guess exactly what's going to happen, all right? Now the point that we're going to use for each of these estimations is the middle of each endpoint. We'll see that there is some unique advantage to doing this. I don't really plan to do any examples with the left and right. Might show up on a simple quiz question or test question. Definitely, I think there's a little bit in the homework, but you should be able to just kind of figure that out. You'll notice what happens here is if I use the middle point of each, then basically what I'll have is boxes like this to approximate the edge. Fill all these in. Let me let you kind of catch up with copying down the stuff. And we'll talk about the midpoint rule. Okay, so the nice thing about the midpoint rule is it also has over and under estimates. But you'll notice that it has a little over and a little under at each single interval. So that way, it actually is a better rule than the other two by far. If you had like an exponential curve that only goes with one concavity, then those under and over estimates should at least kind of balance each other out a little bit at every interval all the way up the line. It's actually mathematically a pretty good rule. It does a good job at estimating areas under the curve. However, the next rule is better than it in the sense that it's just easier to calculate and is equally accurate. So we pretty much never use the midpoint rule. I mean, it has its merits, but not enough to be better than the trapezoidal. But I'll just describe it real quick. Here's what it says. It's trying to estimate, again, the same integral of f of x from a to b. And it says the midpoint rule with n subdivisions, so m sub n, is equal to, a little bit messier to write out than the other ones, delta x times f of x1 bar plus f of x2 bar plus f of x3 bar plus f of x4 bar, where delta x is what we said, b minus a over n. And x sub I bar is going to be equal to 1/2 of x sub I minus 1 plus x sub I. So basically it's saying these averages are just the average of the two endpoints for each thing. So if I look at the first endpoint, I'm saying average out the height of x0 and the x1, and that will be your x1 bar, your height. So this would be like x1 bar in here. This midpoint would be x2 bar, etc. It's harder to write out than just to understand what's going on. You know it's the midpoint, so you can kind of just figure it out. But if you were to write it out mathematically, this is how it would look. Any question with that one? Okay, I'm going to come back at least to do one example with the midpoint rule, but it's going to be just to compare it to this one, which is called the trapezoid. Which, like I said, is kind of better than the midpoint rule in every conceivable way, or at least equal to it, so that we pretty much use this one. The idea of the trapezoidal rule, I'm going to erase, I'll leave it a second. The idea of the trapezoidal rule is the following. Again, we have the same curve. We're going to divide this up into 4 intervals again. And instead of fitting a rectangle in each of these boxes, we're going to try and fit a trapezoid. The reason is a straight line, a flat, is probably a worse representation of what the curve is actually doing than a slanted. So in this first box, we pick the trapezoid that connects the two endpoints on a straight line. Next box, we pick this trapezoid. Next box, pick this trapezoid. Next box, we pick, and that looks exactly like the line. So you have all this area under the curve is your approximation for the real area under the curve. And you can see it looks nice in the sense that, I mean, a lot of these intervals, especially this last one, it's hard to even tell the difference between the curve and the straight line. They're so close. And if you started to make more boxes, instead of 4, imagine you had 20. Now you have like all these little tiny increments, and basically the top kind of looks like a straight line anyway, so you don't expect to be making much error at all. So it actually is a very good method in that sense. It actually looks better than this one, where there's like clear errors. This one actually turns out to be about equally good, just because it's created in such a way that those errors always cancel out. But trapezoidal rule is definitely the first very commonly used rule that we're going to come across. So the whole scheme of this, again, there's the integral of x dx that we're approximating, and we're going to say it's approximately equal to now, we'll call it t sub n. That's trapezoidal rule with n subdivisions, which is equal to delta x over 2 times f of x0 plus 2f of x1 plus 2f of x2 plus plus 2f of xn minus 1 plus f of xn. So it's this nasty summation. I guess I'll just note that delta x, as always, is b minus a over n. And then that whole thing over 2. And then this construction of endpoints, where basically you look at the first one, and then double all the other endpoint heights, and then the last one again by itself. That actually should make a lot of sense, just looking at it. So I'm going to explain it down below. You don't have to write this last explanation, but what is the area of a typical trapezoid? Well, it would be clearly the width, which we're calling delta x, and then it's going to be f of x 0 plus f of x1 over 2, right? That would be your average height, or if you looked at the formula for the area of a trapezoid. So it would be f of x0 plus f of x1 over 2 would basically be that. That's your height that you're looking for. So what happens when we add up the areas of multiple trapezoids to get this whole thing? Well, you'll notice what happens is we have half of the first, at the x0, this endpoint, we have half of that, half of this x1 endpoint, but then the next term would be delta x times f of x1 plus f of x2 over 2, right? This endpoint goes into making both trapezoids, so it gets double counted. So what the trapezoid rule does is basically it pulls out these 2's to the front and says, I count the first endpoint once, the second endpoint, right? All these middle endpoints get twice, 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 all the way until the end, and this one only gets used once. So that's why the formula has those coefficients. That one is, say, an important one to understand. So does anyone have any question with it, or the math or the theory behind it? Online people, you doing okay? In-person people? Okay, so let's actually do a problem. Okay, so we'll compare the last two rules. We use the midpoint rule and the trapezoidal rule. To approximate this integral. To approximate the integral from 1 to 3 of 1 over x dx, where n, that's the number of subdivisions, is equal to 4. I specifically chose this integral because you would know this integral very easily, because it's natural log x. In real life, I mean, we know what it is, and you can plug it into a calculator. But in real life, you basically get natural log of 3 minus natural log of 1. And how do you know what natural log of 3 is? What's the approximation for that? Actually, a computer will probably use the trapezoidal rule using numerical integration to tell you what log 3 is. So there's a lot of different methods and reasons for this. So we can at least compare our answers when we do this. So let's do the trapezoidal rule first, since it's already on the board. All right, first, let me just get delta x, b minus a over n. That's the same for all the rules, it's just the width of each of the intervals. So b minus a is 3 minus 1, n is just always given. The number of subintervals is 4, so clearly 2/4, which is that. So by trapezoidal rule, integral of 1 over x dx for 1 to 3 is approximately equal to, and just copying from there, delta x, which is a half, over 2, which is the constant that we pulled out, times what would be f of 1. And now we know what all these values are, because I know that the delta x amount that I'm going to be going along is just 1/2 a unit. So 1/2 unit past the starting point is 1.5 or 3.5. So plus 2 f of 3/2 plus 2 f of 3/2 plus 1/2 is 2 plus 2 f of 5/2, that's 2.5. And now we're at the end, so we only have a coefficient of 1 at the end, which would be now just f of 3. So that scheme would estimate the area under the curve. But I think we look. What's that?
Will you two f of 2?
No, because that's the last endpoint, right? I don't even know if that's, I don't see it over there. Tricky with masks. F of 3 is the last endpoint. So you'll notice like this endpoint here, when I calculate these trapezoids, right, I need the height at the beginning and end to calculate it. So I use, for the first trapezoid, I use this one and then this one, right? For the second trapezoid, I use this one and this one. Then I use this one, and then for the last one, I use this one and this one. So you see that the first and the last endpoint, the boundaries get used once, and everything in the middle gets used twice. So the beginning becomes a fourth. And then it's just, yeah, just a lot of number crunching at this point, evaluating the function. Function f is 1 over x, so just plugging in, right? 1 over 1 plus 2 times 1 over 3 halves plus 2 times 1 over 2 plus 2 times 1 over 5 halves plus 1 times 1 over 3. Is there any reason at all to do this out? Not really. But you can find a common denominator. If you do that, you're going to get 1/4. This will be 67/15ths if you calculate all these things up. And if you plug that into a long division or something, you get 1.1167. That is what we call T sub 4. That would be the trapezoidal rule estimate with 4 subdivisions. T sub 5 would be something similar. It'd just be 5 subdivisions, so all the endpoints and such would be different.
Is that 1.11 or 1,000?
1.1167. Yes. All right, so how does that look for our first approximation? We'll see how good it does in a second. Yeah.
Why is T sub 4?
Because we're using 4 subintervals. Yeah. So if they had a B part that said, use the trapezoidal rule to approximate this again with 6 subdivisions, we'd call that thing T sub 6. Question online is, okay, so he already got the answer. Yes, I won't spoil it for the in-class people, but we'll get the actual answer in this. Let's do midpoint rule first. So the midpoint rule says the following. The integral from 1 to 3 of 1 over x dx is approximately equal to delta x, which is, I'm not going to write the whole formula out again, just plugging it into it. Delta x, which is 1/2, and then all of the midpoints of each of the intervals. So the first interval goes from 1 to 1.5. So the midpoint of it would be f of 1.25. And then you could similarly find the midpoint of each of them, or you could just add, all the midpoints obviously have to be the same delta x apart as well. So the next one would go from 1.5 to 2. You can average that out to find 1.75, but you can see this adding 0.5 to this midpoint gives you the next one. So f of 1.75 plus f of 2.25 plus f of 2.7. And then that would equal 1/2. Evaluating all these things back into the function, so 1 over 1.25 plus 1 over 1.75 plus 1 over 2.25 plus 1 over 2.75. Skipping all this math, it will come out to be 1.0898, which is what we would call m sub 4. The midpoint rule with 4 subdivisions. Any questions there? Okay, so let's look at the real answer, which someone already found online, but it's a simple integral, right? Like I said, integral of 1 over x dx is just log x. From 1 to 3, you get log 3 minus log 1, which is 0 anyway. So you just get log 3, which is, I'm going to put some more decimal places, 1.0986. So you can see, even with a few subdivisions, right? It's not like we used a supercomputer here for calculations. We got pretty close, right? You're off by what, 0.01? That's not bad. You can imagine what even your simple TI-84 calculator can do. They're probably going to run this, with 50 subdivisions and get as many accurate decimal points for this as you can. If I wanted to talk about the error, okay, the magnitude of the error, we're going to call the error terms E sub whatever the method is. So the error in the trapezoidal rule, so I'll call it E sub t, is going to be t sub 4 minus whatever the real answer was. So that's 1.0986. T sub 4 was this. So 1.1167 minus 1.0986 is 0.0181. Like I said, pretty close. And the error in the midpoint rule is the same idea. I think the absolute value. For our class, we don't really care which way the error is. We just want to see the magnitude of it. So m sub 4 minus the real answer of 1.0986. If you subtract those two and take the absolute value again, 0.0088. Yeah.
I'm confused on how it always got the f of x on the top of the total.
Where the 1.25 came from, or how did I go up? What?
I think I go 1.25 and 1.5.
Okay, so if you looked at this thing, right, from 1 to 3, I'm dividing it up into 4 pieces. So this piece goes from 1 to 1.5, 1.5 to 2, right? So the midpoints would be halfway between those. So anything else on those? Otherwise, we're going to start talking about the error in terms of formula. Now, one thing I should mention is, just keep in mind over the next 10 minutes, I did say that the trapezoidal rule was considered better than the midpoint rule. And here it looks like the midpoint rule gave actually a lot less error. In fact, it gave about half the amount of error that I got in the trapezoidal. We're going to see why that's actually not significant at all to us as we start talking about what the error is expected to be. I guess I just want to put one thing before we talk about what's called an error bound. Is clearly the way to get less error, right? Suppose I said, here's your results. I really wanted it accurate to within 4 decimal places. The way to do that would be make smaller and smaller subdivisions. So basically more subdivisions overall, basically increasing the n, and that would get you better and better results. So I'm going to just say as a general rule, to decrease the error, you're always going to opt for increasing n, which is the number of subdivisions. Okay. Now, we are able to solve for the actual error here, because we use the calculator to get what is log 3, whereas the calculator actually uses this method to figure out what log 3 is. So that really isn't, that's a circular thing. How do we actually know how good of an answer our approximations are from scratch? And to do that, we have something called an error bound, which we're not really going to prove out in this class, but if you take the next class on this subject, which I think be Math 340, a very interesting class. If any of you are computer science majors, that's a very, very good class for that. It's called Applied Numerical Methods. It's all about implementing mathematical models and formulas and schemes and seeing and proving what type of error they would be expected to have. So that's just something for the CS people. But in doing so in that class, they are able to prove out error bounds, which is basically the maximum that the error could possibly be using a certain method in a certain number of partitions. So the maximum the error could be in using a method. And they're actually really important because that allows you to say, all right, I know exactly how much error I'm making. You could say, look, I want my error bounds to be smaller than 0.0001. What is the n that I would have to use to achieve that goal? Once you do that, then I say, well, now I know that the answer is correct up through those 4 decimal places. So that's pretty much how people and how calculators and computers figure out the right answer to things. They're just approximating like you and I, but they basically used an error bound and said, look, I'm going to spit out 8 decimal points in my answer, and I've already proven to myself that I know it's accurate to 8 decimal points. So here are the error bounds for these 2 methods. Suppose, first of all, we're going to need a constant k. K is the maximum value of the magnitude of the second derivative of x on the interval, magnitude of the second derivative of x on the interval that we're doing the approximation interval, so that would be a to b. And furthermore, just a notational thing, in E and T and E and M are the errors in the 2 rules that we've been talking about lately. So these are the errors in the trapezoidal and midpoint rules. And here are their error bounds. And a lot of ratings. Second. Okay, so the error in the trapezoidal rule is less than or equal, and it's the magnitude of the error, I don't care about the sign in this particular case, is less than or equal to k, which I defined over there, times b minus a cubed over 12n squared. K times b minus a cubed over 12n squared. And similarly, the error in the midpoint rule is less than or equal to k times b minus a cubed, also. Denominator is slightly different, over 24n squared. Notice that this actually makes a lot of sense because you'll notice that they are exactly the same except for this coefficient in the denominator. The midpoint rule's coefficient being twice as big so that this is twice as small overall. And that's exactly basically what we saw, right? The error in the midpoint rule ended up being almost like half of what the error in the trapezoidal rule was. That seems like significant things for most of us, like first thought, but it actually is not really considered important. These coefficients are really not the driver from a computer programming perspective of how the error behaves. The real thing that's interesting is the n. And the n is the same in both cases. They're both order n squared. That means if you double n, the error should go down by a factor of 4. So the same amount of extra work will give us the same amount of improved accuracy for both methods. The reason a computer programmer, by the way, prefers this one to this one is because all down the line, there's an extra step involved in the midpoint rule. You have to calculate the midpoints. Whereas here, you just use the partition points. So that's why from a programming perspective, this is more complicated. And those extra calculations you have to keep doing is way more important than the fact that the coefficient is slightly different, considering the fact that the n power is exactly the same. Okay, one more note with this. I really should ask if you've got any questions, though. Someone here might have one. Does that mean the midpoint rule is technically more accurate? Yes, I would say it is technically slightly accurate in what I would refer to an insignificant method, right? It's insignificantly more accurate. How about that? But it is significantly less from a programming perspective. Now here's an interesting one. If f double prime of x is equal to 0, what would happen to the error bound? Notice k is the maximum of f double prime of x. So if f double prime of x was 0, your error bound says the error will be less than or equal to 0, which means it's perfect. There will be no error at all. So the error bound is literally equal to 0, so we would have a perfect approximation. What types of curves would have a second derivative that is 0? Or what curve has a second derivative of 0? Mm-hmm. Any linear curve, right? Any straight line at all. So I'm going to say there's this perfect approximation of any line or any linear function, probably a better way to write it out. You don't have to write this down, but it actually makes a lot of sense. Imagine I had a straight line, right? And I'm going to divide it up. It doesn't actually matter how many divisions, because n is going to be irrelevant at this point. The numerator is 0 anyway. So even if I used a single one partition, would it be perfect using both of these rules? And the answer is yes. Look at the midpoint rule first of all. It would be the width times the midpoint height. But because it's linear, this error in here is going to be perfectly balanced out with that error in there. So no matter if you divide it up into 20 little elements, they're all going to balance each other out. Even if you just use one, it's going to balance each other out. Even more obvious is the fact that the trapezoidal rule is perfect. Because even using one interval, what is the shape of this thing? It is a trapezoid. So you would just say, find the area of that trapezoid. That's the end of the curve. If you broke it up into a lot of little trapezoids, each single interval is a trapezoid. So you'd find the exact area by these methods for anything that is linear. So it's kind of like an interesting insight, because I think it's very interesting to understand where these things come from and not just randomly memorize two error rules. Right, any questions with that? That's why I picked something with a log function, because this one's a little more interesting. So let's look at the bound for the error of the function that we're looking at. Bound the error in using these two methods. Actually, let's just do trapezoidal rule. So bound the error in using the trapezoidal rule to approximate the integral from 1 to 3 of 1 over x dx with n equals 4 subdivisions. So it's important to know the difference between the bound of the error and the error. What we did before was the literal error, the actual true answer minus the actual approximation. This is just a bound of the error. It's saying, I don't know exactly what the error is going to be, but by math, this is the worst it could possibly be. It might not be exactly that amount, but it's going to be something less than that potential. Okay, so I guess we should write down what f of x is. All right, we're going to be plugging into this formula. The first thing we need to figure out is the k. F of x is obviously 1 over x. And the k is the maximum of the second derivative on the interval. So I'm going to have to take the second derivative and then figure out what its maximum is going to be. So f prime of x is negative 1 over x squared. F double prime is negative 2 comes down, so I get positive 2 over x cubed. And my k, I'm just going to write this in words, it's going to be the max of f double prime on the range 1 to 3. So what is the biggest that the second derivative can be on the range 1 to 3? First of all, I guess, what value of x would make it the maximum? You got 1, right? Because I'm dividing by it. So if I divide by the smallest thing, that would make this the biggest possible, right? If I divide by 3, it's going to make the second derivative small. So the maximum of it is 2 over 1 cubed. You should have absolute value around that, but here it's all positive anyway. So the k in this case is 2. Notice that that's going to depend on your interval range and your second derivative of those two pieces. Say again? So this is the function, right? Mm-hmm. I'm saying what value of x could I plug into this that makes this the biggest possible? So I can see if I plugged in 2, I got 2, right? If I plugged in 3, I'd get 2 over 27, right? A lot smaller. So is there anything on this range that would be bigger, or make this bigger than if I plugged in the smallest value? The answer no. Almost, I would say, every single problem in math 112, the answer is going to be one or the other, the endpoints. It's technically possible for the answer to be in the middle somewhere, but that would be a very weird function. Let's do the error bound over on this side. Okay, so E of t is going to be less than or equal to, I'm going to rewrite the formula, k times b minus a cubed over 12n squared, and we can fill all that in now. Where k is 2, we just found that. B and a are the endpoints, so 3 minus 1 cubed over 12. N is your number of subdivisions, which we gave as 4 squared. So, I mean, it's pretty easy to figure all this stuff out, right? This is basically 2 cubed is 8 times 2 is 16. 4 squared is 16 times 12. Might as well just leave it factor because the 16s cancel. And I get 1/12, which is equal to 0.08333. And again, the importance of this thing is this is the biggest that the error can possibly be. We already know the actual error because we calculated it using even our calculator. The actual error was this for comparison. The actual error was 0.0181, which is obviously quite a bit better, right? If I told you without knowing anything, look, I'm potentially off between plus or minus 0.08, and in the end I ended up being off by less than 0.02. But that's what an error bound is, just the worst case scenario. Okay. Any question with the concept of the bound? Feel good about it? Okay, so again, we're just kind of comparing it to reality, but again, suppose we couldn't know what the reality was, and we really need an approximate area that's more accurate than 0.08. Here's how we can do a problem and say, I'm going to confirm that I'm definitely below a certain error. So in that case, we just have to figure out what the sample size would need to be in order to achieve that error. So I'm going to write the problem here. We'll do it on the other side. The question, the B part, is how large should we make n, the number of subdivisions, in order to guarantee the following results. So to guarantee that the error in using trapezoidal rule to approximate this integral that we've been dealing with the whole time, to approximate integral of 1 over x dx from 1 to 3 is under 0.0001. I say there's no such thing as a calculator. I just need to know that the error is less than that, and then I'm happy. Okay, so we're going to work it out on the other stuff. Okay, so in this case, it's solving the exact same inequality that we had before, except there's a different unknown. I know basically what my bound has to be, 0.001, and the unknown has to be the n. So just solving a different algebraic equation. So I can say E of t is less than or equal to a times b minus a cubed over 12n squared, which is less than, right, the error bound has to be less than this error. I want to absolutely assure myself, essentially, that I've made an approximation that's good to that degree. So plugging everything in, I get k is still 2. It's the same range and everything, same function. B minus a cubed is still 3 minus 1 cubed, so it's still 2 cubed. 12 is still 12. And squared is what I'm looking for. And just a simple equation to solve for. Well, it's n squared, multiply across over there, so it's 2 to the 4th, 16 twelfths. I guess, yeah, divided by 0.001, less than n squared. And then if I did this out and square rooted it, I will get the answer. So the thing I get here is 6666.6 is less than n squared. And if I took the square root, I get 81.6 is less than. So basically I have to do more than 81.6 subdivisions. However, of course, I can't do like a tenth of subdivision. That doesn't make any sense. I either do a subdivision or I don't. So you have to round this number up. Okay, so round up. So n has to be greater than 82 subdivisions for the desired accuracy. And so any questions there? Looking good so far? So I got a problem for you to try out with these two in a second. But first I got a quick random question. I feel like things are a little less personal because most of us are online, everyone else here is in mass, never really get to chat. So I happened to see this news article, I gotta ask your opinion about it. So there was a survey done that said that they interviewed college-age students and said, would you spend a week in jail in exchange for forgiveness of your student debt?
Yeah.
You're for it?
Absolutely.
Everyone here is for it, yeah?
That's the security.
No problem, right?
Absolutely.
Now, they did a B question for the girls. Someone said no here, though. Let's see. Oh, no, they're all yeses. Yes. Big yeses, capital letters. B question for the girls. Girls can answer online. I'll ask Nora here. And actually, we got two. Would you shave your head for forgiveness of student debt?
Yeah, I do it.
Yeah?
Yeah.
Yeah? Same? You guys there too? No, for the guys, it doesn't count. That's an easy one. I'm gonna give a different one for the guys. This wasn't on the official poll. Rosenardi says it can grow back. Exactly, right?
Yeah.
For forgiveness of debt, that's like a no-brainer. For the guys, I'll make it a little harder. Would you lose a pinky?
Absolutely.
Yes?
What do I use them for?
That's true, yeah.
Hey, do I get to pick which one?
Yeah, sure.
Alright, cool. Absolutely, no problem.
This one's more controversial. I got 4 no's, 2 yeses.
It depends on the pain.
Uh,
If it's like a lot of pain.
well, like, are they gonna put anesthesia and do it nice, or is it gonna be like an alligator? All right, so for the people that are yes, most of you guys on no, yeah, they're all no, they want their pinkies. So how much can we take with the debt? How many fingers, or if we start eating away at your body?
I would give everything. You know, you can have this whole hand. That's as far as I'll.
The non-dominant hand.
Yes, I'm taking a non-dominant.
That's pretty, and you would do that?
Yeah.
Wow, he'll take a whole hand off. Just one finger here.
You can replace.
Nicole would give up her firstborn child. Wow.
That's amazing.
That's bringing back the Roman way, right? Sell them to slavery. Which I'm actually reading this book about ancient Rome. It's very interesting. A lot of people do that, like their first child, sell them into slavery, or like sell them to an aristocrat. They'll pay for the rest of the kids. There you go. Rough life, huh? So one person said they want to lose a pinky toe, but good point. That actually does mess up your balance. Interesting. All right. So for the girls, you do pinky?
No, not the pinky.
Not the pinky.
No.
But the head, yeah. All right. Interesting, right? Get to see how people's minds work. Last semester, not last semester, over the summer, I had seen this poll, so I actually saw it. And some of the girls were adamant even about the hair. They're like, absolutely not. That's my hair. I don't know if it's gonna grow back weird. I'm never gonna do it.
It must not have a lot of or
Yeah, I
And it
mean,
grows back.
yeah, I agree with you. All right, so I'm gonna give you a question to do. Try and do a little bit more, question of the days here and there every once in a while. The question for you is to estimate the integral 0 to 3 of x squared dx with just 3 subintervals, so n is going to be 3. And you're going to estimate it by the trapezoidal rule. B, you're going to calculate the error bound for this approximation. And C, you're going to find the actual error that was made. So what I'm going to do is, for you guys online, I'm at 9% battery. That should probably take me to the end, but I'm going to put up the answers just in case. And if I lose you, just try and get to them. That's going to take us to the end, so I'm going to stop recording here. These are all the questions. You're going to estimate this integral with trapezoidal rule, then calculate the error bound, and then find the actual error. Dave wants to keep his hair, because that's his moneymaker on TikTok. Good for you. Always a backup plan. Do you really have 10,000 followers on TikTok? Really? Okay. What's your most amount of views? One of my tutors in the tutoring center, 1.6 million, for real? Oh my God, I gotta look this guy up.
Professor.
Yes, Marco.
What's the quiz on for tomorrow? Is it just the rest of the integrals like trig sub and I forgot the others what they're called?
Yeah, so I think it's going to be a trig sub because technically I have your partial fractions homework due Wednesday in case you didn't get to it. I'll just make it a trig sub problem.
Just the one?
Yeah, they're long, right?
Oh yeah.
Yeah. But do you want more? I mean, we can.
No, I'm fine. I'm fine. Yeah, okay. Yeah, okay.
Don't ruin the first, Marco.
Thank you, Professor.
Trouble. Yeah, so you should be finding that the second derivative here is literally 2, right? So this is an interesting case where actually any value of x you plug into that, I mean, it is always 2, so the max is 2. And that's the reason why the error bound ends up being exactly what the error is. Because the second derivative never changes, So the rate at which you're accumulating error, what in other cases it does, it says, let's assume the worst case scenario for every interval. Well, in this case, 2 is the worst case scenario, and it is there for every interval. So that's why the error bound becomes exactly the error. So, fun little details on this stuff. Let me get him. Okay, yeah.
Is there a way where, or like, how do they come up with the error bound formula?
That we cannot do in our class. That's for Math Report. So they will prove that out. The way you use it or prove it out is something called Taylor series expansion of formulas, of functions. And we will learn Taylor series later. Actually, yeah, you know that. We don't really know how to apply it to functions, but it's basically, if you take that class, it's almost like applied Taylor series. And that is how they write out the terms and figure out all the cancellations, and they come up with these formulas. All right, so you guys good online? Otherwise, I'm gonna end this off, I guess. I will see you guys on Thursday for the rest of this. There's one more rule. Otherwise,
Bye, Professor. Have a nice day. Stay safe. Stay healthy.
you too. Bye.
Have a nice day, Professor.
Bye. Cool.